Everybody of the High Energy Density Science Center Seminar Series. I'm pleased to have with us today Dr. Jim Bailey, who received his BS in physics from the University of New Mexico in 1978 and a PhD in physics from the University of California, Irvine in 1984. Following a postdoctoral appointment in the physics department at Lawrence Livermore National Laboratory, he joined the Pulsed Power Sciences Directorate at Sandia National Laboratories in 1985. He's currently a distinguished member of the technical staff at Sandia, and Dr. Bailey's primary research interest is high energy density physics, with an emphasis on spectroscopy and the behavior of atoms and plasmas. His research has spanned a wide range of topics: Z-pinch radiation hydrodynamics measurements, X-ray microscopy of cells, spectral line emission absorption diagnostics, ion beam matter interaction experiments, 1 gigavolt per meter electric field measured with the Stark effect, and capsule implosions driven by Z-pinch X-rays. His current research concentration is in laboratory measurements of astrophysical plasma properties. Dr. Bailey was elected a Fellow of the American Physical Society in 2004 and is a member of the American Astronomical Society. He is a 2-time recipient of the Lockheed Martin Nova Award, and in 2016 he received the American Physical Society John Dawson Award for excellence in plasma physics research. So please be aware also this is an unclassified meeting, and be aware of any export control issues since we have people logged in from all over. And if you have any questions, if you're here in person, I'll pass you the mic after Jim's talk. And if you're online, please enter your questions into the chat field. Otherwise, I hope everybody enjoys, and please take it away.
Great, thanks, Paul. It's great to be back here in Livermore. And today I'll be talking to you about laboratory opacity measurements for stellar interiors. Of course, I have many collaborators in this work, including a group of people at Sandia, University of Texas at Austin, the French CEA laboratories, Lawrence Livermore, Los Alamos, University of Nevada at Reno, Prism Computational Sciences, and the Nuclear Research Center of the Negev. A theme for today is that laboratory measurements imply photon absorption in high energy density matter is different than previously believed. Just to remind you, photon attenuation by matter is called opacity, and X-ray opacities govern energy flow in stars like the sun. X-ray opacities at stellar interior conditions can now be measured for the first time, and what we're finding is a complex mixture of agreement and disagreement depending on the conditions, temperature and density in the plasma, and depending on the element that we study. So there's a lot of physics that we can learn from this. What we're doing are holistic studies with high energy density experiments and theory, and we feel like that is a way of progressing to help stellar astrophysics. What we need to understand is a broad range of elements at temperatures between about 100 and 1000 electron volts and densities between about 0.1 and 1 times solid density. Shown here on the right is a little cartoon of the sun and also the opacity that's contributed by different elements. So you can see you have to study a lot of different elements. And one thing to keep in mind is that for an L-shell element like iron, there's billions of bound transitions that have to be included. For something like K-shell oxygen, there's far fewer transitions, but there are density effects that have to be taken into account. So both are interesting. We've done experiments on chromium, iron, and nickel. We've varied the temperature and density to look at trends. We've made multiple repeated experiments. And one of the things we started over the last few years was time-resolved measurements that I think are teaching us quite a bit. We've also started oxygen measurements, and now we're doing experiments on different platforms. So there's a group of people here at the NIF that we collaborate with to do comparable experiments on the NIF as what we're doing on Z. From the theory perspective, there are investigations of line shapes, 2-photon absorption, simultaneous electron-photon collisions, and transient localization that people are investigating at different institutions around the world. And we feel like we have to continue this collaborative scrutiny in both experiments and theory to fully understand the behavior of atoms in these extreme conditions and solve the solar problem. And I'll tell you in a minute what the solar problem is. So this is my outline. I'll give you a little bit of a motivation on the solar interior problem. I'm going to skip over the part about what physics is a concern for opacities. There's experts here at Livermore that know a lot more than I do about what the physics really is, but we can talk about it at the end. But I had to skip something because there was just too much material to include here. I do want to describe how we do the opacity experiments and some of the opacity results. And then the results, what you're going to see is that there's this model data discrepancy. The question is, how can we resolve that discrepancy? So the solar problem is that standard solar model predictions of solar structure disagree with helioseismology. And this has been the case now for about 20 years. Standard solar models use inputs of things like abundances, equation of states, opacities, and they make predictions that can be compared with helioseismology, which give very precise measurements of things like the boundary location between the radiation and convection zone, density profile, and the sound speed profile. The problem really arose starting around the year 2000 when the abundances were revised that people think are in the different elements in the sun. And in particular, the amounts of carbon, nitrogen, and oxygen were lowered by between about 30 and 50%. That work of the abundance determinations has continued, and I think it's fair to say that it's somewhat controversial. And I think as time goes on, those abundances will go up and down to some level. But the outcome was that when they lowered those abundances, the standard solar model then disagreed with the helioseismology inferences of both the convection zone base location and the sound speed and density profiles. And shown there is a plot of density as a function of radius. And you can see that the percent difference between the these model calculations here were with the old abundances, and this is with the new abundance. And you can see that right around the convection zone boundary location, there's now this big disagreement. The solar problem could be resolved if the true mean opacity for solar matter is 10 to 30% higher than predicted. Shown here is a calculation of opacity as a function of wavelength. And this is for the complete solar mixture of about 20 different elements at the convection zone base conditions, which are around 182 electron volt temperature and 9 to the 22 electrons per cubic centimeter. So the old abundances are the black curve, and the new abundance is the red curve. And you can see that the Roslin mean, which is listed there in black and red, decreased by about 20%. And that affects the solar structure in a way that it means that the model predictions don't agree with helioseismology anymore. And just to remind you, that's the equation for the Roslin mean opacity. And just to remind you that according to that, photons are transported in the windows. So it's really the places where the opacity is lowest that you care about. Iron opacity measurements can help determine if the opacity model inaccuracies really are the explanation or if it's something else. So here's a calculation of opacity as a function of wavelength. And it's the same red and black curves as what I had on the last slide, but now I've superimposed the contribution from iron, and you can see that the part of the spectrum where iron contributes is between about 5 and 16 angstrom. So it's the L-shell contribution from iron that really matters. And the plot on the histogram on the right there is the opacity fraction for different elements calculated with the CEA model OPAS at the convection zone base conditions. And you can see that the elements that make the biggest difference at the convection zone base are iron and oxygen, followed by neon. So it makes sense that we should investigate iron, because iron not only has a strong contribution, but it's also complicated. It has a lot of bound electrons, and so the theoretical approximations that have to be used are difficult. And I just want to mention that our the way we look at it is that our stellar research really continues an endeavor that began about 100 years ago when Eddington and his colleagues first realized in the 1920s that opacity is important for stellar structure. Now, at that time, and for about the next 40 years until the 1960s, all people included when they modeled stars was the bound-free opacity. In the 1960s, people realized they should include the bound-bound transitions, and that made a big change in the opacity. Opacities really weren't measured in the lab for high energy density matter until the 1980s when Steve Davidson from AWE and Ted Perry started measuring opacities for aluminum at that time and on laser facilities like the Helen laser in England and the Nova laser here at Livermore. In 1990s, there were theoretical advances made by scientists here at Livermore that helped to resolve the Cepheid variable problem, where people, astronomers, couldn't explain the variation in the Cepheid variable output until the OPAL model was constructed that explained that the opacity was really 2 to 3 times higher than what people had previously believed for the envelopes of these variable stars. Then we came along starting about 15 years ago now. We started measuring opacities for iron, and we're still at it. It's quite difficult to make these measurements, and we still have a lot to learn, but we published our results in 2015 that identified a disagreement with theoretical models. So just a bit about strategy. Our strategy is that we're going to make wavelength-dependent transmission measurements to test the opacity model physics. So what the astronomers really want is the opacity from all the elements so that they can construct a Rossland mean from the solar mixture. We measure what they call the monochromatic opacity, so the opacity is a function of wavelength, because all of those bumps and wiggles, all the spikes and the valleys that you see there are carrying the information about the atomic physics. So if we can decode that information, we can test how well we understand atoms in these conditions. So how do we do that? Well, one question is, how come people didn't do it before? So if opacity was recognized as important for stellar astrophysics a century ago, why weren't laboratory measurements done before? And the overarching requirement is that you've got to reach the temperature and density and the radiation field that exist inside a star. So you've got to produce that in your laboratory for uniform, well-controlled enough conditions for macroscopic enough samples. So the samples have to be around long enough and they have to be big enough that you can make accurate measurements. That's one part. The second part is that you need a backlight that's bright enough to overwhelm the sample self-emission so that you can measure the transmission. As you make the sample hotter, the self-emission goes up, and so you need a brighter and brighter backlight to overcome that. So high accuracy at those conditions requires large facilities and disciplined technique, and that includes now the megajoule class facilities like Z, NIF, and I believe also the LMJ should be capable of these kind of measurements. We're also using 3 decades of opacity research that started here in the 1980s to hone our technique, and advanced plasma diagnostics as well that have been developed. And I do want to mention that I think future experiments at short pulse lasers like the Orion laser in England and at X-ray laser facilities like LCLS, the European XFEL, and at SOCLA in Japan will further advance opacity knowledge at these extreme conditions. Now, benchmark quality opacity experiments have a lot of requirements that are demanding, and I won't go through this entire list. You can look at it on the slide, but it's a long list of difficult to achieve experimental problems. In principle, it's simple. The sample opacity is inferred by measuring a backlight with and without a sample. So the shown on the left there is a backlight that's just traveling to a spectrometer. And then next to it is a backlight that's traveling through a sample. So you measure the unattenuated spectrum, B sub nu. You measure the attenuated spectrum, I sub nu. You can plot those as function intensity, as a function of wavelength. You divide those two, you get the transmission, and then you convert the transmission to opacity by taking the natural logarithm and dividing by the areal density. There are some sources of uncertainty, which are how accurately do you know the unattenuated intensity, and how accurately do you know whatever background you've got in the plasma, and then finally, how accurately do you know the areal density or the sample thickness. The experimental challenges that you face in those kind of measurements are platform dependent. On the left is what we call approach 1. That's an area backlight. That's what we do on Z. And in that approach, we have a plasma that heats the sample, and then we split the sample into two sides. One side has the element that we're interested in, iron, for example, and the other side just has a tamping material. We place various apertures and slit assemblies on top of that, and we observe it with multiple spectrometers. In fact, we have 6 spectrometers that we use in each experiment nowadays. The advantage of that approach is that the background tends to be rather negligible. The difficulty is that it's harder to measure the unattenuated spectrum accurately. Now, in contrast, approach 2, or point projection, which is what's used here on the NIF and was used in prior laser experiments, measures the backlighter through a whole realm, and in that experiment, you simultaneously can get the attenuated and unattenuated spectrum with high accuracy. The problem is that now you've got a small backlighter for a short time, and so the background tends to be higher relative to the signal, so that's the challenge. For us, though, the experiments I'll be describing today, the main challenge is to get the unattenuated backlight intensity accurately. So how do we do that? Well, we have a spectral image that's resolved in both space and wavelength, and that really provides the essential information that we need. So you can see there's a Z-pinch radiation source. It's propagating through a sample that's split into one side that's unattenuated, one side that's attenuated. There's spectrometers at different angles that are observing that backlight spectrum that either comes through the sample or not. And because there's some separation, the place where the backlight center appears relative to the boundary between those two halves is different on this different spectrometer. So you see a -9 degree spectrometer sees a different spatial distribution of the X-rays than a +9 degree spectrometer. So you can take lineouts shown in red there through in the spectral direction, and that's what's shown in this plot here. And you get an intensity that's roughly the unattenuated intensity, and then the attenuated is shown in red. But you can also take space direction lineouts, like what's shown in green there, where you get a boundary at the location of the iron. So we use that spatial shape to improve our accuracy of the transmission analysis. So this again is one of these space resolved spectra. So this is actual data here that's got, you can see the iron lines and the magnesium that we add to diagnose plasma conditions. And for example, if you have a backlight intensity that's shown here in red, and it's propagating through a sample that has some certain transmission, and transmission drops when it reaches that boundary, then you get a spatial distribution that looks like that plot there in the upper right. So what we do is we search for the transmission that will give us an attenuated spectrum that's adjusted to match the measured backlight calibration data. And we do that at each wavelength. So we do that at a bunch of wavelengths throughout the spectrum. And of course, the challenge is, well, how do you know what the unattenuated backlight spectrum spatial shape is? And we measure it over and over again over many years. And for example, this is 48 spectral images from 12 calibration shots. So it has some distribution. So we use those calibration statistics to provide the uncertainty in how well we infer the transmission. What we wind up with then is a probability distribution for the opacity. So that's this 3D plot there, that where you have the probability of the opacity and it's a function of wavelength. And that gives us uncertainties at each wavelength that we want to look at. So the result of that was that in 2015, we had 3 experiments with one particular temperature and density that I'll describe in a minute that agreed to within 20%. In 2020, we redid that same measurement, but then with 9 experiments using this new analysis approach. And then in that case, there was plus minus 10% agreement. And we've been working on it for the last 3 years to further refine the approach and to do more experiments. Now, the method accuracy can be tested using all of this calibration data. So this is an example of all the different actual measurements from KAP crystals. We have 62 independent measurements. We also have data taken with RAP crystals that are another 19 measurements. So this is intensity as a function of wavelength along the horizontal axis and space along each vertical axis. So you can convert each of those actual measured calibration spectra into what we call a synthetic data by taking a transmission that's calculated by some opacity model. You multiply that transmission by your calibration measurement, so that then converts it into something that looks just like our data. And the question is, well, why are we using the real data? The reason is that when you have real calibration data, it has all of the quirks and the warps and the problems that come in any experimental measurement. And so you can analyze that just exactly the way you analyze real data that was taken with iron. And you can do that over and over again to infer whether your accuracy that you think you have is really what you have. And when we do that, this is an example where the inferred transmission is in blue, and the correct answer, because we know the correct answer because we multiplied that transmission by the calibration data. So we do that, in this case, 20 to 50 times, and then that tells us a formal uncertainty for how accurately we know the opacity. So where we are now is that we've developed these methods. We're still in the process of testing them, but the next step will then be to apply them. This is an example of 19 experiments in iron taken with one temperature and density. So 75 data sets. We have to analyze 450 spectral images, but then we're going to apply these new methods to all this data, and we think that's going to give us the most accurate answer that's ever been obtained for an opacity measurement. And I'll just point out that we don't have just that one condition, we have multiple conditions. So we have 42 iron experiments in addition to experiments taken with other elements. So we have a lot of data to analyze. So that's how we get the opacity, the transmission, and then we get the opacity. Well, what about the plasma conditions? I just want to mention a little bit about that. The way that we infer temperature and density is by mixing magnesium in with the iron. And then we use K-shell spectra from the magnesium to get the density from Stark broadening, shown there on the left, and the temperature from line ratios, shown there on the right. One important thing that we do is that in order to change the conditions, we make very simple changes in the sample design. So on the left is what we call anchor 1. That's a design where the sample is tamped by 10 microns of plastic on the top and the bottom. The tamper suppresses the expansion of the sample so that the time that it's backlit, it's reached a certain density. And because it can't move away from the source, because the tamper is there, that keeps the temperature high as well. So that sample design gives us these conditions shown on the left of, it's really 155 to 167 EV, depending on the exact experiment, and density of about 7 times 10 to the 21 electrons per cubic centimeter. We make a very simple change, which is to add 35 microns of beryllium on top of the sample. So the beryllium provides more suppression of the expansion, so the density is higher at the time the backlighting happens, And in that case, we get a temperature of about 184 eV and 3 times 10 to the 22 per cubic centimeter. And I don't have a cartoon for it, but we have another configuration that we call Anchor 3, which uses an even thicker tamper to get a temperature of about 200 eV and a density of about 5 times 10 to the 22 per cubic centimeter. We're in the process of refining the temperature and density analysis as well. And there's two aspects to that. One is that we're using a new line shape model that was constructed by Thomas Gomez, and we believe that that is an improvement over previous line shape models, in particular Merle, which we've used for a long time, and also the total model, which was originally constructed by Dick Lee. And you can see there the approximations in the different models, where the new model that Thomas Gomez put together has removed now most of the approximations that the previous models used. The plot on the right is a line shape for the magnesium helium gamma line, and that's the Merle calculation is in green. The red calculation is the total model from Dick Lee, and then the blue is the new calculation by Thomas Gomez. Is actually somewhat in between the other two models. So if you apply that to some experiments, then what you find is that in comparison with our Merle-based analysis, the density goes up and the temperature also goes up. The second part is that previously we used a multi-line fitting method where we would fit all of the magnesium lines simultaneously, and we think that we get a more accurate answer by fitting the individual lines separately and exploiting the physics that we know. So for example, if we know there's 3 lines in the spectrum that are sensitive to density, then we fit those lines first and get the density, and then we move on to measure the lines that are going to give us a temperature ratio. And we think we get a more accurate answer by doing that, and we think we get more accurate uncertainties in particular by doing it that way. So we're in the process of applying this also to the data. So now what about some results? Shown here is a plot of opacity as a function of wavelength. The top plot is what we called the Anchor 1, which was the first result that we published back in 2007. And this is a comparison of our data in red at 156 eV and 7 10 to the 21 electrons per cubic centimeter. And the blue model calculation is from the prism spec model. And what you can see is that the agreement is not perfect, but it's darn good. It really is extraordinary how it's capturing all of the bumps and wiggles in this data. I still think there's quite a bit to learn about the Anchor 1 conditions, because there are statistically significant differences between all the model calculations and the data, but nevertheless, it's quite good agreement. What we realized when we published that data was that the ionization distribution was similar to what exists at the base of the convection zone, but the temperature and density were so much lower that we needed to raise the density and temperature in order to be able to evaluate the solar problem. And what happened when we did that was shown on the bottom. That's an Anchor 2 measurement at 182 eV and about 410 to the 22 electrons per cubic centimeter. And now the data in red is much higher than the model calculation. And that's the data that we published in 2015 in Nature. And if that result is correct, it accounts for about half of the opacity increases needed to resolve the solar problem. The question ever since we published that, though, is, well, why is it that the data is so much different than the model calculations? And in order to help answer that question of, well, why does this discrepancy exist, we think it's helpful to divide the discrepancy into different categories, because different aspects or different approximations may explain the different problems. So in other words, it may not just be one reason why they're different. So we divided up into the continuum, which you see there at the shorter wavelengths or higher photon energy. There's the fact that the windows are lower in the models than they are in the data. And then the bound lines tend to be fatter in the experiment than they are in the calculations. So since that 2015 publication, we've been working on our analysis. We've been doing more experiments, and this shows you our present best effort analysis. So the black now is the OP model. The red is our newest analysis from 2020, and the blue was what we published in Nature in 2015. And you can see that the difference in the quasi-continuum is smaller, but the error bars are smaller also. So the discrepancy is still about at 3 sigma there. In the windows, the data stayed about the same, but again, the error bars have shrank. So now the discrepancy is even bigger than it used to be. So as I mentioned, we're in the process of applying these new analysis techniques to this collection of, we have 19 experiments at these conditions now, and we think that when we publish that data, that it will be our best effort of what we can measure. So in the next 2 to 3 months, the temperature density will be reanalyzed, and the opacity of all the iron data will be reanalyzed with these refined methods. We have a total of 6 experiments for anchor 1, 19 experiments for anchor 2, and 11 experiments for anchor 3. And then there's another category of even different conditions where we have a variety of a few different experiments. So we think that reanalysis will help solidify our understanding of these. It won't necessarily answer the discrepancies. So once we had that iron result, one of the things that we realized was that by doing a systematic study of opacity as a function of atomic number, we could constrain hypotheses for what was causing the discrepancies. What we did was we did experiments with chromium and nickel, because chromium has more vacancies than iron, so that we thought might pose an even bigger challenge for theoretical models. And nickel, on the other hand, is mostly a closed shell element at these conditions, so it's mostly neon-like. It should, in principle, be easier to model. What we found was published in this PRL in 2019 was that the measured lines are broader, and that's a case at the top there is shown, and that's a nickel 2p to 4d line. The window filling was found to exist in both iron and chromium, but not in nickel. So that suggests that the window filling may be related to the L-shell vacancies that you have. And the quasi-continuum was only seen in iron and not in chromium or nickel, which is difficult to understand because it's not a monotonic thing. So either the experiment has an undetected flaw in iron at these conditions, even though iron at the lower temperature and density doesn't seem to have this flaw, so it's not the iron itself, or the theory is missing some physics. An example could be two-photon opacity. So anyway, these systematic study results are guiding our current investigations, and I just wanted to remind you some about this puzzle with the nickel 2p to 4d line. I think it's interesting because the left plot there shows the data from 5 different experiments. That's the normalized opacity line shape, or actually that's not even normalized. That's just what came out of those experiments. The thickness of the orange line there is our experimental resolution. Shown on the right are 4 different model calculations for that line, and you can see that the models are all different from each other. And what we found was that most of the models don't agree with the data, even for this relatively simple neon-like line. The one model that does agree is the SCO RCG model, which is a hybrid statistical detailed line model from our colleagues at the CEA. And what they've told us is that they believe the reason they're getting this agreement is because of their treatment of the satellites that are next to the parent line. So I think it's an open question whether that means that other lines might have similar problems in the plasma. Is this a unique thing for this particular line or not? I think it's an interesting question to investigate in the future. Now I want to say a little bit about our work with time-resolved measurements, because one of the suggestions that people have made is, well, could temporal gradients be responsible for the discrepancy that we've got at anchor 2? So we wanted to measure the opacity as a function of time. It turns out that it's easier to measure the temperature and density as a function of time as a starting point. So that's what we did first. We're in the process now of trying to measure the absolute opacity as a function of time as well. The impact of temporal or time-resolved measurements, though, is even broader, because it can help us to understand how the experiment works better. And if we can understand it better, we can refine it and make even better measurements. So we want to perform the time-resolved experiments. We want to minimize that concern. In principle, then we can get opacity measured at multiple conditions in a single experiment as the conditions change. And we should be able to measure opacity at a higher density and a higher temperature, conceivably. So how does it work? Shown on the left there is a photograph of our spectrometer. It's being lowered into place with the 20-ton crane. So this is a big operation. There's 6 spectrometers, and 2 of them are equipped with these ultra-fast X-ray imagers that were developed at Sandia. And shown on the right is just an example of some of the data that we get, where each frame there is resolved in space and in time and in wavelength. And we're able to measure, I can't remember what our record is. It's around 10 or so frames of this type of data on a single experiment. So each of those frames, as I mentioned, is resolved in space and time. And in our experiment, there's a radiating shock that's moving inward with time, and that's in the dynamic hole realm that we use to drive the experiment. I don't have time to explain that today, but the radiation propagates through our half-moon sample, and so we see time 1, time 2, time 3, that shock is propagating inward, and you can see the spectral lines. Those are magnesium lines that we use to infer the temperature and density. So we can make those measurements as a function of time and then infer temperature and density. Here's the results that we got for anchor 2, and this is from 7 different experiments. The temperature is a function of time and density is a function of time. And you can see that, in fact, the temperature is increasing with time by what I would say is not a small amount, going from about 120 eV up to 205 eV. And the density is also increasing as a function of time. That was a surprise because it contradicted both our intuition for how the experiment works and previous simulations that were published, where the density is expected to fall with time as the sample is expanding. Seems logical. And the temperature was predicted to peak and then fall. So one of the interesting aspects of that is that the measured density, even early in time, is an order of magnitude lower than solid density. So it means that the sample was subjected to some kind of preheat that caused it to expand before the backlighter started in our experiment. That made us realize that if we could get rid of that preheat, we could probably do experiments at even higher density than what we've done up to now. Another thing to notice is that the density and temperature at the time that the backlight is peak agrees with what we had previously inferred from film-based diagnostics. So, but the picture that we have for how the sample works has to be revised compared to what we used to think. One question is, well, why is the temperature increasing? Is it that the source and the sample are moving closer together? Or is it just that the heating and cooling rates are such that the sample is continuing to heat even though the radiation is decreasing? The density is low, probably means there's some kind of preheat. The fact that the density increases with time, we think is likely because the plasma from below, that the Z-pinch plasma is actually pushing and applying macroscopic pressure onto the sample. Well, what about the question of the temporal gradients? To estimate the effect of the temporal gradients, we need to have the backlighter temporal shape, which we measure, and we need to measure the temperature and density as a function of time. And if we combine those together, we can infer the attenuated spectrum at all the different times. We can add those spectra up and compare them to the spectrum that you would calculate just at the peak of the backlight time. And that's shown in red. So the red is essentially the film integrated opacity, and the blue is the opacity that's at the peak time. And what you can see is there's very little difference. So the implication is that temporal gradients don't cause the discrepancy that we're seeing. Now you can still try and do this better, but that's the result that we have up to now. And I just want to point out there's one limitation here, which is that we're using a theoretical model calculation because we have to calculate the opacity at all those temperatures and densities as a function of time. So if those opacities are incorrect, then that could impact our assessment of the time-resolved temperature and density gradients. And so that's the work that we're doing now, is to measure the opacity, the actual absolute opacity as a function of time. Now, I think I'm running a little short on time, but I do want to mention the oxygen measurements because I think they're both important and interesting. Oxygen opacity measurements are essential to resolve the solar problem. Shown here is opacity as a function of wavelength, and that's now you can see the iron that we've been working on is shown in blue. The solar mixture is in black, and oxygen is in red. Well, oxygen is actually the strongest contributor at the base of the convection zone. We didn't pick that to start with because it's a simpler atom, and we thought it would probably be better understood. And also, it requires that you make measurements out to longer wavelengths than what we could at the time. So there were a couple of reasons to start with iron, but we really think that regardless of what the outcome is for the iron, the discrepancy between the models and the data, in order to solve the solar problem, we have to measure oxygen, because if iron measurements are lower than, if iron measurements are higher than the predictions, but oxygen measurements are lower than the predictions, then they might counterbalance each other. Or if it goes the other way, it might be that oxygen and iron combine to explain all of the solar problem. So we really need to know what the result is for oxygen. Oxygen is simpler than iron because it has fewer bound electrons. But what that means is that since oxygen is either hydrogen-like or helium-like or bare in the sun, if you have a very small change in the ionization, the bound-free opacity will change a lot, because it's either zero, it's going from something that's has some value to something that's zero, right? If it's completely stripped, then it's zero. So that means that oxygen can be more affected by things like continuum lowering, because that can affect the ionization distribution. Now, to measure oxygen, you not only have to make measurements at longer wavelength, but you also need accurate temperature and density. So shown here is opacity as a function of density at 14 angstroms for oxygen. And on the left is a plot of density, on the right is a plot of temperature. And you can see that the variation in the opacity is fairly significant as a function of those plasma conditions. So it means that if you want to know the bound-free opacity at 14 angstroms to within 10%, you've got to know the density to within about 12%, and you've got to know the temperature to within about 2%. So that's a challenge. We infer the temperature and density with silicon line transmission. And what we found is we've now made, I think, 5 experiments at what we call anchor 1 conditions for oxygen. And our very first comparisons are shown here. These were done at what I would say a visual inspection analysis of the temperature and density. So a density of about 8 10 to the 21 and a temperature of 160 eV. So the black is the data, and you can see 4 different model calculations, and the models are lower in the bound free, and you can also see that there's some discrepancies in the amount of continuum lowering, because the data has a stronger Lyman gamma and Lyman delta line than what the models predict. You can also see that the models are different from each other. So this is just an enlarged view of that same data. So that was at 160 eV temperature. But if we actually do a more careful analysis of the silicon lines, it indicates that the temperature is lower, more like 142 eV. And if you use those temperatures and densities, now the model calculation, this is a Scram calculation, it agrees with the bound free. You still have the discrepancy in the Lyman gamma and Lyman delta, but now we have a big discrepancy in the Lyman beta that didn't exist before. So I have to say, we don't understand exactly what's going on here. It does seem like there may be some refinements needed for the oxygen, and we have to work to further refine our temperature and density analysis, because the range from 142 to 160 is significant. Let me just say that we're doing experiments now where we mix magnesium in as well as the silicon to get another alternative temperature and density diagnostic. And we're using a different type of temperature inference that uses satellites that have an initial state that's from an excited state. So I think those are both things that are going to help us to refine that. But at the moment, I don't think we're ready to say whether there is or isn't a discrepancy and exactly what the nature of the discrepancy is. But it looks interesting, even at those relatively low temperature and density conditions. Now, recently, we also did a couple of experiments at higher temperature and density, and this is just the raw data that's shown here, and you can see that, in fact, the oxygen Lyman beta line is getting fatter in these high density measurements. So I think that data is going to be interesting. And we also did one experiment that was aimed at measuring the spatial gradient. So this is the type of experiment that we did a long time ago for iron, but now we think we need to redo these experiments for oxygen, since the oxygen samples turn out to be very thick. Since the opacity for oxygen is low, you've got to put a lot of it. And so we feel like measuring the gradient through the sample is going to be important. So we put aluminum on the bottom, magnesium on the top, and we'll look at the temperature and density inferred from those different elements and evaluate whether they are at the same temperature and density or not. So I'll just finish by mentioning a few theoretical ideas, because it's not my area of expertise, but I'm very interested in the work that's going on around the world to try and resolve this discrepancy that we measured. On the upper left there is a 2-photon absorption that there's 2 groups that have been working on that. One, Dick Moore has led, and the other one that Michael Cruz and Carlos Iglesias have led here at Livermore. There's this idea of simultaneous electron-photon absorption. And you can see the reference there. It was PRL from 2020 from a group at Imperial College. There is an idea called transient spatial localization that was published from some people in China. They've now published maybe 5 papers or so on that. And there's also some ideas about the contributions from satellite lines that were published by our colleagues from the CEA laboratory in France. And then there's also questions about how to improve the approximations that are used for line broadening. And shown there is a PRL from Thomas Gomez, and also this paper from some people from the Hebrew University. I'll just mention that preliminary 2-photon theory calculations indicate that 2-photon absorption cannot be ignored in inaccurate HED opacity models. Shown on this slide are different cartoons for different mechanisms that need to be included. On the left are 2 mechanisms. There's bound from an initial ground state in the neon-like atom That was calculated both by Michael and Carlos using what I called the Delgarno-Lewis method. I'm not sure if that's the right thing to call it. Michael, you can correct me if that's not right. And the perturbation theory method. Those results agree that the effect is small for that particular mechanism. There's also been calculations of bound free, so ionization, where you start from a bound state and you wind up with a free state going through a virtual state. And the calculations from perturbation theory and the Delgarno-Lewis also agree in that case. But the mechanisms on the right, I think, have only been calculated with perturbation theory. That's where you have a bound-bound transition from an initial excited state, but the bound-bound transition is going through a virtual state. So that's where the two-photon part comes in. There's also Raman anti-Stokes and Stokes contributions. And at least according to the perturbation theory, those contributions are significant for Z conditions in the 9 to 15 angstrom range. So since it's 9 to, I don't know if you remember the range from about 500 slides ago, but that means that if these calculations are right, this mechanism will not explain the discrepancy in the quasi-continuum, but they might explain part of the discrepancy in the window filling area. So I think this hypothesis needs more investigation. I think we should compare it with all the data that we have, so chromium, iron, and nickel, not just iron. And we should search for direct experimental tests, not these more indirect tests. And I just want to mention that in all these cases, our Z experiments, the way I think about it is the experiments can inform the theory models, but we really need theory. We're never going to do all the experiments that we need to understand the inside of stars. So the impact is really arising over a broader range of conditions and not just the conditions of the experiment. Okay, I'm going to leave you with this long list of 18 takeaways. First, there's 42 iron experiments that we did over the last decade on Z. We're in the process of refining those results. The temperatures range up to maybe a bit above 200 eV, and densities in the 4 to 5, 10 to the 22 per cubic centimeter. Analysis refinements in progress are providing formal uncertainties that are benchmarked against calibration data. And our present best effort results still retain the iron model data discrepancies at about the 3 sigma level in the quasi-continuum and more than 10 sigma in the opacity windows. The measurement range presently spans 5.5 to over 20 angstroms. And what that means is that I think we can make the first measurements that will actually test the sum rule, which not that people are necessarily worried about whether the sum rule is valid or not, but I think this will be the first experimental test. The nickel data shows that most models have difficulty predicting widths, even for relatively simple features like neon-like 2P to 4D. The chromium data shares the iron opacity window discrepancy that suggests some kind of model difficulty for open L-shell ions. And the combined data from different atomic numbers, temperatures, and densities can provide powerful hypothesis constraints, whatever they might be. The time-dependent temperature and density measurements are different than what was predicted by simulations, but a preliminary analysis shows that the temporal gradients have little impact on the results that we published that were based on film-based detectors. Experiments exploiting the time-resolved data to achieve higher density measurements are already in progress. I didn't have time to talk about those, but we can talk about it later if people are interested. The first oxygen opacity measurement suggests that model refinements might be needed, but we need to substantiate those initial results. And the initial oxygen measurements at higher temperature and density have already been performed. And we also did this experiment to measure the oxygen spatial gradients. I think theory investigations, my perception is they've really strengthened the field, but they've not yet resolved the Z model data differences. Two-photon opacity seems to be too big to ignore based on perturbation theory, but You can ask, well, is that theory correct or not? And I think we need more theoretical work and more experimental research to evaluate that. The satellite line broadening, TSL, and simultaneous electron photon absorption hypotheses all probably merit more investigation. And work is in progress to compare Z and NIF results, and I think that's really going to strengthen our opacity knowledge even more. So I'll stop there. So thanks.
16 through 18.
Hi, that's really interesting to hear the proper detail on that. So your theory about the density increase in the sample, have there been any simulations of that, of like the full, like the Z plasma hitting into the expanded sample and then recompressing? Do the simulations show that like
Yeah, I think the question was about the fact that the density is going up with time, and so there's a hypothesis that the Z-pinch plasma is pushing hydrodynamically against the sample. And that idea actually arose out of simulations that a fellow named Tom Nash did at our laboratory about a decade ago. I don't remember if he ever published those results. He attempted to see if he could parameterize the amount that it would affect the density, but the problem is that we don't know. The experiment is not good enough. So in other words, in order to do that accurately, you need to know how much pressure and how fast that plasma is moving, and we didn't have measurements that would support that. So I think conceptually it's a good idea to do those simulations, but I'm not sure that simulations by themselves are accurate enough without guidance from experiments, where the guidance has to be dedicated measurements on the pressure. So I don't know if that answers your question. I think you asked whether simulations had been done or not. The answer is yes, but they support the qualitative idea, but not the quantitative amount. I would say that if that's not happening, I don't see how the density can possibly go up with time, because if the density is going up with time, it means that the sample is not expanding, and yet we know the sample is at 150 to 200 EV depending on the experiment, so it has to expand.
getting more dense? That's, yeah, peculiar otherwise.
Right.
So, hi, Jim. That's an excellent presentation and a great experimental data set. I was wondering if in your time measurements of the temperature, you saw that the temperature increases. Did you have a long enough range that you also saw the cooling? And if you did, how was the cooling rate compared with the calculations?
Yeah, so again, the question was about this time the temperature increase, and there are a couple of experiments that suggest that the temperature is going down at the last time frame that we measure. We're not sure yet if we fully trust those results, so that the status of those results is that Guillaume is doing a final analysis of temperature and density right now, and part of that will be evaluating whether we should trust the temperature that's lower late in time. So one thing to appreciate is the time span over which we're making these measurements is really extraordinary compared to what one might have expected. So the time resolution with that detector is 1.9 nanoseconds, and the full width half max of the backlighter pulse is 3 nanoseconds. So what it means when I say we're measuring from 5 nanoseconds before to something like 4 nanoseconds after, that means we're down at the 1% level of the backlighter. The only reason we're getting any measurements at all is that the UXI detector seems to have an extraordinary signal to noise. The data really, they're just fantastic. At the peak of the backlighter, it's probably better than the film data. So that probably doesn't exactly answer your question, but it gives you a flavor for we're not exactly sure whether the temperature goes down. I'll mention one other thing, which is important for discriminating between different ideas for why the temperature goes up. So there's this idea that, well, maybe the X-ray source and the sample get closer together because the X-ray source is moving upward with time. We should be able to tell whether that's happening or not because we make parallax measurements with two time-resolved detectors that are viewing from two angles. So you can measure the boundary of the sample relative to the center of the backlight and see whether they seem to be getting closer together by looking at the parallax. We haven't finished that analysis yet, so we're not sure what the answer is, but that's our hope, is to be able to tell whether it's that or whether it's something just to do with the heating and cooling rates being compatible with the temperature going up. If it's the heating and cooling rates, it means that the simulations have to have the wrong heating and cooling rates, right? Which could be, but I don't know.
Thank you. There are a couple of questions from online. One of them is from Burkhard Militzer, who says you quoted the earlier solar abundances by Asplund in 2005, but not the later higher value published by Asplund in 2009, or Lauders in 2009. Is there a reason for quoting the earlier work?
It's just an older slide, Burkhard, but let me point out, the Asplund group published a new paper in 2021 or 2020 or 2021, and the title is something like Solar Composition, a 2020 Perspective or something. You'll see it if you look for him. There's also a new paper by, I'm not sure how to pronounce the name, is Mag or Magi or Mag, and they are also inferring abundances that are closer to the old Graves and Saval 1998 abundances. So they're still lower than the 1998 ones, but they're in between the Asplund and so those two groups don't necessarily agree with each other. There's also a really interesting paper that you might look at on the solar neutrinos, where people tried to use the solar neutrinos that were recently published. And I can't remember the author's name, but I could send you the reference. But what's interesting is that they try to infer the composition by looking at different flavors of solar neutrinos. And their conclusion was that, that it didn't support the Asplund abundances. But if you read through the paper, what it says is that there's an ambiguity because they have to assume an opacity in order to connect the abundances with the neutrinos. And the result they get will so if the opacity is not accurate, then they can't make that discrimination. So it's all interconnected. I don't really see that the solar groups are going to continue arguing over abundances. They've been doing it for 50 years, and I don't see any reason why they should stop. And I think presumably they're going to get more and more accurate. But I think we have an opportunity to really help them by measuring these opacities because they're so interrelated with all the other inferences that people can make. And it's something that we can measure in the lab that you can't necessarily measure the solar photosphere composition in the lab.
Thank you. And there's a quick question from Sean, I don't know the last name. It says, does the Gomez quantum model include line shifts?
It does have a line shift. And whether our data can measure the line shift accurately enough to tell whether the model prediction is correct is something that we need to look into more. I don't know the answer. Our spectrometers are not necessarily calibrated to give us accurate line shape positions because that wasn't what we intended them to do. But it could be that by using things like known edge positions or other line locations that are not predicted to have any shifts, that we can calibrate our wavelength scale accurately enough to see whether the shift prediction that is made in the Gomez model is accurate or not. I think it's something that's been controversial in the line shape community pretty much for my whole career. And just as an anecdote, I remember as a graduate student, I was reading a paper by, I think he was either Belgian or French, Drouin, and the title of the paper was The Final Word on the Plasma Polarization Shift. Maybe Brian remembers, but people are still discussing whether they can treat it correctly or not.
Thank you. I think in the interest of time, we should cut it off there. But otherwise, thank you everybody for attending, and hope to see you back next time. And let's thank our speaker again.